Excuse me. Let's go and get started. So first off, let's take care of a little bit of housekeeping. So first off, in regards to homework, you all have homework 6 due today. So hopefully I've got some packets of homework up here. If you haven't turned that in, go ahead and do so. Homework number 7 is our next homework assignment, and that's on Mohr's circle and combined loading. So that's basically everything that we've been talking about, you know, the stress analysis, stress transformation, and then up and through Mohr's circle and combined loading that we're going to talk about next. Keep in mind, when I mention analysis of stress and stress transformation, principal stresses, it's all kind of the same topic because it's all about orientation and whatnot. So that homework assignment was uploaded today. It is going to be due after break, okay, on the 29th. I made it due on the 29th so that on the 27th we could bring it up again and make sure everybody has questions. Now, I want to be absolutely clear that homework assignment is going to cover mostly stuff that we talked about last time, stuff that we're talking about today, and stuff that we're talking about on our online lecture on Thursday. I think there's one problem on thin-walled pressure vessels, but when we talk about pressure vessels, you're going to see that it's actually a really short topic. Like, the problems are really simple because it's a very plug-and-chug topic. It is probably the most plug-and-chug topic that we have in our entire course. You know, here's the stresses, plug-and-chug, and here's your answer. So it's pretty straightforward. As for just remaining homework throughout the semester, you have homework 7, which is due on the 29th, and I believe on the 29th, yeah, it is on the 29th, I assign you homework 8, which is on our final topic of the semester, and that's elastic buckling. That's going to be due on December 6th, the day of our exam review, and then we are done with mechanics of deformable bodies, other than obviously the final. So that's it, okay? One other thing, let's make sure everybody is clear. We are not having a physical in-class session on Thursday. What I'm going to do is I'm going to post a video on YouTube, and that video is just going to cover combined loading. Combined loading, I think you're going to see there's not a whole lot of new stuff associated with combined loading because it's basically just using stuff that we've done before and throwing some stress transformation stuff in there. So you'll see when we watch the video how if there's any one lecture we were going to have online, this would be the one to have. And I'm doing that just because this is the day before break. I figure give you all a chance to get early on some turkey, or get early on eating some turkey. So, sound good? Okay. So I want to go back and review some of the mathematics that we discussed in regards to stress transformation. I'd argue that of any of our topics, this is probably the one that's the most math heavy, and I do apologize for that. It is what it is. There's really nothing I can do about it. But I try and relate it in a setting that's familiar, that's easy to recognize. So let's say I have a state of stress, right? So I analyze the structure, and I got some stress this way, some stress that way, and I got some shear stress. The first thing that we wanted to ask was, well, what happens if, you know, I've cut the section this way and I've got some stresses? What happens if I cut the section this way? What happens if I change my orientation? What happens if I change the orientation of my coordinate system? Well, I think after last time, I think we pretty much well established that the stresses that we compute are a function of the orientation that we choose at the beginning of the problem. And if that orientation changes, our resulting stresses are going to change. And we have this expressed, you know, in these formulas, but we also looked at that in this problem here. So we have a stress state, you know, and that stress state is just based on a x-axis going to the right and a y-axis going up. And we said, well, what happens if you take your coordinate system and you rotate it? Okay? What happens if you do this to it? What happens to the state of stress? Well, the state of stress changes as a result. And we did that problem last time, and we got something about like this. So we changed the orientation of our stresses, or of our coordinate system, and that ultimately changed the resulting state of stress. Instead of 6, 10, and 5, we got, you know, 9.04, 5.04, and 6.28. Like the values changed. And we saw that even, you know, a couple different ways beyond just this specific example. First off, if you take this specific example's initial state of stress and you plot, well, what happens if you really start changing those orientation angles? Because we're dealing in sines and cosines, you really start changing your stress states quite a bit. So here I have the state of stress plotted in example 28, and over here on the y-axis, this value, let's see if my pen's going to work, this value here, here, and here, those were the initial states of stress given at the beginning of the problem with the orientation at 0. This was as we computed them. Well, if you change that angle of orientation, you get a new state of stress. You get this, you get this, and you get this. So you get an entirely new state of stress dependent upon a change of orientation. So this is looking at it, from a trig perspective. And then we also had this animation that we looked at, which did something very similar. Here's the state of stress initially. So, you have a stress in the x direction that's minus 120, a stress in the y direction that's positive 50, and a shear stress of positive 100. And as that orientation angle changes, the state of stress changes along with it. So is everybody okay with that concept, like just that by itself? The idea that if you have a state of stress and you change the orientation of the way you're looking at it, if you change the orientation of your coordinate system, the stresses are going to change as a result. Everybody okay with that? All right, any questions? Okay, all right. If you're okay with that, then let me close this. I want to look at this plot a little more closely, and I want to look at this point here. This point here is a very, very interesting location on the coordinate system. Now, first off, what is our angle of orientation here? Well, we have an angle of orientation here that's something like, I don't know, what is that, like 75 degrees, something like that. There's also another similar location right here where the answers are very similar. In fact, that we're getting the same normal stresses, it's just flipped. And this is something like, what was it, like 165, something about like that? Yeah, something similar. Okay. At these orientations, something very interesting happens. And it happens simultaneously, which is a really unique phenomenon. Not only at these locations do we get zero shear stress. See, here is this dotted line here, that's the shear stress profile. And you can see that at both of these locations, the shear stress is 0. Okay? Well, not only does that happen, not only is the shear stress equal to 0, but if you look at the normal stresses, what do you find on the normal stresses? The shear stress equals 0, but what's the deal with the normal stresses? They're at their maximums, or their minimums, depending on if you're looking at positives or negatives, but they're at their extreme values. Okay? So that is going to present a very interesting analytical challenge for us. Okay, so what we're observing at this location, this normal stress here and here, we have a particular name for that. We got to start coming up with some terminology. So we call those principal stresses. So if you want the term, what is the term principal stress? The principal stress is, there's two ways of saying it. One way of saying it is the principal stress is whatever the normal stress is when the shear stress is 0. Okay, as is the case in this plot. So shear stress equals 0, that and that are my principal stresses. Shear stress equals 0, that and that are my principal stresses. Okay? So that's one way of looking at it. Another way of looking at it is they are the absolute maximum normal stress values that you get. Okay? So how do you determine these values? Well, let's just go back to basics. How do you determine a maximum on a curve in general? Like, how do you determine an extreme value? Go back to good old Math 229. You take the derivative, right? So we're going to take the derivative. Now we're looking at normal stresses. Okay, so I'm going to take the derivative of one of these normal stress functions, and I'm going to take the derivative with respect to the angle, because I want to determine at what angle do we get worst case scenario. So here's my function for sigma 1. That's one of the normal stresses. I'm going to take the derivative of that. I'm going to set it equal to 0, and I'm going to solve for the angle. Okay. Now, let me walk you through the math a little bit so that everybody's clear on what's going on. So here's my function, okay, I know there's a lot of alphabet soup here, but I want to illustrate this. So I have, we'll simplify it a bit. I have a pile of junk plus a pile of junk plus a pile of junk, right? Keep it simple, right? Now the derivative of a sum is the sum of the derivatives. So what about that first pile of junk? I'm taking the derivative with respect to theta. That red curly bracket right there, are there any theta terms there? No, so that's like taking the derivative of 3. What's the derivative of 3? 0. It's a constant. If you're taking the derivative with respect to theta, then everything else is a constant. So taking the derivative with respect to theta, this term goes to 0. What about this blue term? Well, what's the derivative of the cosine of 2 theta? We got to break out that chain rule, right? Remember that? So we take the derivative of all the stuff on the outside times the derivative of all the stuff on the inside. So what's the derivative of the cosine? Nope. Negative sign. Negative sign. And there we go. So we have the cosine of 2 theta, so the derivative of that is going to be minus sine of 2 theta, but then we have to take the derivative of the inside. What's the derivative of 2 theta? It's 2. So we've got this, so minus 2 sine 2 theta, so we have the 2 there. So that's how I'm getting this term right here. So how did we go from, the blue bracket up top to the blue bracket on the bottom? Well, we have a minus 2 sine 2 theta, that's the derivative, and then so that's where that minus is, and the 2's cancel. Everybody okay with that? As for what's going on the blue, or on the green bracket, we have a constant times the sine of 2 theta. What's the derivative of the sine of 2 theta? Well, it's the cosine of 2 theta times 2, right? So that's how we got that, this, and that's why that is positive, okay? So that's how we went from green bracket to green bracket. All right? Now, what am I going to do? I'm going to set those terms equal to one another, and I'm going to solve for the angle, okay? So what do? All right? I set this equal to 0, so let's add this over, okay? And then I can divide. Well, what is the sine of 2 theta divided by the cosine of 2 theta going to be? The tangent of 2 theta, right? That's sine over cosine is a tangent. So if I reduce this a bit, I get the tangent of 2 theta is 2 times tau xy divided by this. Well, if I'm solving for theta, plug and chug, and that's what I get. So that theta value is what's called the principal orientation. Remember, as that block rotates, we get different normal stresses and shear stresses. Well, that's the magical angle such that we get maximum normal stresses. Okay, and so we call that the principal orientation. So, theta sub p. So if you're wondering where the p comes from, that's the principal orientation. That's the orientation to generate worst case normal stresses. Okay, sound good? All right. Now here's what happens. Okay, now I'm doing a little bit of magic here, so let me go back a little bit. See this angle? Okay, we're going to take this angle, we're going to plug it into this and this, and we're going to simplify. That's a whole lot of alphabet soup. Okay, because imagine taking this angle, putting it here, 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 and here, and evaluating. I could show you that if you want, or you could believe me when I tell you that that's the answer. Okay, so you end up getting a sigma 1 and a sigma 2 after you plug in that angle. Because you're actually taking the sines and cosines of these angles, the trig functions go out. So you get a sigma 1 and a sigma 2. Notice how I'm using Roman numerals. So those Roman numerals are the absolute worst case scenario principal stresses. And the nice thing about the principal stress formulation is that the formula is actually pretty easy. The method to determine principal stresses is not bad. It's pretty straightforward. And when we tie this to Mohr's circle, you're going to see how it's really simple. So, Mohr's circle makes this very, very easy. So, just so everybody's aware on our notation, this is why I use the notation as is. So we have sigma x and sigma y. Those are the stresses as they're given to us. We have sigma 1, sigma 2 with the numerals. That's our new orientation. Like if I have sigma x and sigma y and I rotate it a little bit, that's a new stress state, so sigma 1, sigma 2. What is the sigma Roman numeral 1, the sigma Roman numeral 2? Those are my worst case normal stresses. Okay? Everybody all right with this? Okay. So, let's go back to that stress state, and let's see if we can determine the worst case principal stresses and also determine the orientation of that stress state. And I'm doing that for a reason, because I want to relate that to some of the previous graphs that we've done. So remember, we have a positive 6, a minus 10, and a minus 5. So let's see how that works. So here was our initial problem. We had sigma 1, sigma 2, and tau 1, 2 based on a following orientation. Now let's determine principal stresses and orientation. Oh. Okay. Let's determine principal stresses and orientation. First thing I'm going to do is I'm going to look at the orientation. So the orientation, the principal orientation is determined as follows. So, excuse me. So we have a half times the inverse tangent of 2 tau xy over sigma x minus sigma y. Okay? So that's 1/2 inverse tangent. We have a fraction. So sigma x and sigma y. Well, sigma x is 10, sigma y, or sigma x is 6, sigma y is minus 10. So that's 6 minus 10. And then we have 2 times, what was tau xy? What was that? Minus 5. That's 1/2 inverse tangent of, so on the top that's minus 10, on the bottom that's 16, right? So minus 10 over 16 is minus 5 over 8. Now, what is that? You should have Casio FX115 ES pluses or similar computational devices. Negative 16.0. Do I have a second on that? Okay. Now, that doesn't quite match what we got on the graph, but let's remember one of the first things that we discussed when we looked at orientations, right? Remember, we're dealing with trig functions, right? So we would think that they would rotate every 360 degrees. But not only do they rotate every 360 degrees, they rotate every 180, right? Remember, we're seeing a lot of 2 thetas in these expressions. And also, if I have a section and I samurai sword, right, or I Judy chop right through the section, whether I cut this way or I cut this way, it's still the same section at the same orientation. So your stresses are going to repeat not only every 360 degrees, but every 180 degrees as well. So what I'd like you to do, take that value and let's add 180 degrees to it. If you add 180 degrees to that, what do you get? Say it again. 164 degrees. Do I have a second on that? Okay. Why did I do that? Well, here's why I did that. what should we have gotten? Well, I don't know about you, but the graph tells me it should have been about 165, right? Isn't that what we got? You know, we got like 164. I'm not that good on drawing straight lines, but I'm close. So, everybody okay with that? Okay. Now, here's another thing. Let's see if we can interpret these graphs a little bit. Okay? What should our maximum stresses be? So what are we getting for the top value? What is that, about 7 something? What are we getting for the bottom? About 12 something, about like that, right? Let's see how that works. Okay? Let's see if that works. All right? Does everybody have all of this? Okay. I'm going to go to the next panel. We are at 50 pages on our notebook. Can you believe that? 50 pages. All right. So as for our principal stresses, so the formula states that we have sigma 1 and 2 equals the following. We have sigma x plus sigma y over 2 plus or minus the square root of sigma x minus sigma y over 2 squared, and then plus tau xy squared. Okay, so there are two principal stresses. Okay, typically when you compute principal stresses, the first principal stress is taken as sigma x plus sigma y over 2 plus this square root. And then the second one is taken as sigma x over 2 minus that square root. All right. So remember, sigma x is, what was sigma x? Was it positive 6? Yeah, positive 6. Sigma y was minus 10. And tau xy was minus 5. So what I'm going to have you all do is compute these out. Tell me what you get for the first one. Pretty much. Pretty much. This is a very plug and chug process. As long as you get it, yeah. What do you mean? I'm going to get to that. I'm going to get to that here in a sec. I'm going to get to that. That's a good question. And it'll be easy to explain here in a quick second. Calculator out. What's that? 3.39? I'm getting something a little different. You might want to check. All right. 7.43. That's what I'm getting. I'm getting 7.43 for this first one. Check your signs. Are you getting it, or? Let me make sure I have the formula written correctly. Yep, I do. Let me see. see. Well, hold on. It's not 6 minus 10. It's 6 minus negative 10. Use the fractions. Use the little fraction button. I do want to make sure everybody's getting this, so. Everybody getting it? Okay. All right. Does that match what we got on our plot? Let's see. Let's pull up our plot. Does that match what we got on our plot? That's pretty close. I mean, I wasn't using a straight edge or anything, but that top value was somewhere around the 7 range, and that bottom value was in that sort of 11 or 12 range. Actually, if I had drawn that a little straighter, I'd have probably gotten it a little closer. But I can't draw a straight line to save my life, so. Okay. All right, so everybody okay with that? And again, does that match what we got before? Well, yeah. I mean, we know our orientation angle is about like 164, which is about what it should be. And if you drag that out, that's about 7, and that's about 11.5. Now, what you were asking, why didn't you get this angle? Well, you could if you flip your sigma x and sigma y. That's the only difference. So, because remember, your tangent functions repeat every 90 degrees. So yeah. Okay. Everybody all right with this? Okay. Now, you like my little spiffiness here? I had to work hard to create this. I know I'm lying. I found this online. But if you recall, we've been seeing a whole bunch of sines and cosines and enough trig to make you go crazy, right? But if you recall, what is the sine function and the cosine function? Well, another way of expressing it is that the sine and the cosine are nothing more than the x and y coordinates on a unit circle, right? If you want to plot the points on a unit circle, it's the x-coordinate is the cosine and the y-coordinate is the sine. So can we take all this trig and make it a whole lot simpler? Yeah. Okay. We recognize the relationship between sines, cosines, and the plotting of a circle. And I think you can probably see where this is going. Okay. So we can develop a very similar relationship for a state of stress, and there's a particular name for it. We call it Mohr's circle. Okay. So here's what's going on. Let's go back to basic fundamental pre-calculus. Did you all do this in pre-calculus? I don't know if they cover what. No, just the graph of a circle. Just circles, right? Do you cover that in algebra or pre-calculus here? I actually don't know. Is it 132? Probably both. Okay. Well, the standard plot or the standard form for the equation of a circle is as follows, right? You have x minus h squared, y minus k squared. Add that up, gives you r squared. R is the radius of the circle, and then h and k, those are the coordinates of the center, right? Okay? Now, what I've got here is I've got our equations for the state of stress, and I've rearranged them a bit, okay? Please, you can write all this stuff down if you want, but this is going to turn into some alphabet soup. I'm just going to go ahead and tell you, okay? If you look at this term, we have x minus a value, and then that quantity is squared, right? Well, over here, I have stress minus a value, and then that quantity is squared. So what I'm going to take with this first equation and this second equation is I'm going to square them, okay? So remember foiling, first, outside, inside, last. I'm going to foil this and foil that. So it's going to get nuts, okay? So bear with me. So if you take that quantity and you foil it, you get this. And you take that quantity and you foil it, and you get this. I know it looks a little crazy. Just bear with me. If you take this and you recognize that some of these terms can cancel if you add them up. Because if I take this equation and I add it up to this equation, well, if you FOIL it out, what happens is this whole term here and this whole term here cancels, right? If you do that, and then you look at the other terms, well, if I add this and this, basically it's just that times this and that times this, so I can just add these up. Well, what is the sine squared plus the cosine squared? It's 1. What's the sine squared plus the cosine squared? It's 1. So after you FOIL all this out, what happens is a lot of this crap cancels, and all the other stuff that adds up has sine squareds and cosine squareds, and they all add up to be 1. So what ends up happening is you have a very nice little plug and chug relationship to graph that circle out. Specifically, what happens to plot the equation of this circle is as follows. We compute what's called the average stress. The average stress is just sigma x plus sigma y is 2. And then we plot the radius of that circle. What is the radius of that circle? Well, look at this equation, right? We have x minus h squared plus y minus k squared equals r squared. This is r squared. So the radius of that circle is just the square root of all that hullabaloo there. Okay? Then we plot the circle as follows. And I think you're going to find that the plotting is really simple. In fact, if you look at these equations, they should be really familiar, because what is sigma average plus or minus r? Well, it's sigma x plus sigma y over 2 plus or minus that, right? We literally just used that like 10 minutes ago, right? That's the principal stress equation. So what you're going to find is that if you have a state of stress, Mohr's circle will make your life so much easier in determining other states of stress. And we're going to explore that here in a second. Okay? Let's take this state of stress and let's do what we've been dancing around this whole time, and let's draw Mohr's circle for this state of stress. Okay? And I think you're going to find this is really, really simple. Okay? So I'm also going to try and maybe use some of my little drafting tools here and see if I can make this work. So we'll see. Okay. C, Mohr circle. So here's what I would propose. Part A was really hard. Part B was easier. Part C, really easy. Watch this. Sigma average is sigma x plus sigma y over 2, which is 6 minus 10 over 2. What's that? Minus 2 KSI, right? The radius of this circle is, okay, so what is that? It's the square root of sigma x minus sigma y over 2 squared plus tau xy squared. What does that come out to be? Say it again. 9.43. Do I have a second on that? You do. All right. Okay. Now, right off the bat, before we draw Mohr's circle, let me show you something. You can compute sigma 1 as saying sigma average plus R, and sigma 2, principal stresses, as sigma average minus R. And if you chug that out, you're going to get, plus 7.43 and minus 11.43. Whole lot easier than our previous two steps, right? Check this out. All right, I'm going to leave this up here. Does everybody have this? Okay. All right. Bear with me. Oh, no, that's not what I wanted to do. Okay. Okay, so I'm actually using the sort of the straight line tool here. Okay, let's see. Okay, so remind me, what was sigma average? Minus 2. And what was the radius? Okay, all right. Let me redraw this a bit. Hold on. Give me a sec. I apologize. I want to give myself a little more room here. Okay. Let's do this. Okay. So what we're going to do is we're going to draw this out, okay? And this x-axis is going to be the normal stress. And this is going to be the shear stress. Okay? And what we're going to do is this, okay? We're going to, actually, let me move this over a bit. There we go. That's what I want. Okay. What we're going to do is we're going to utilize these points here and here to draw the circle. And it's really simple. All we're going to do is the sigma average is how far we go on the x-axis. Why is it how far we go on the x-axis? Because we're plotting normal stresses on the x-axis. So we're going to start at minus 2. So let's say that minus 2 is right there. Okay? Then what we're going to do is we're going to draw a circle from that location with a radius of 9.43. Okay? So let me see how I'm going to do. Okay, that's how it works. All right, so we're going to draw a circle. Let's make it like a red circle. Let's draw a circle. That's not red. Okay, so that's 2. What do you think 9.43 is? You think that's about a radius of 9.43? Is that about right? Is that okay? I propose that that is Mohr's circle for this state of stress. And we're going to do some really cool stuff with this, okay? What do I mean by that? You said this is sigma is minus 2 KSI, right? What are the coordinates of this point? This point right here. Now, how'd you get that? Plus the radius. I propose that this is sigma 1. Pretty cool stuff, right? What about sigma 2? This is sigma average minus the radius. So that's, all right, make sense? But look at this from a circle perspective. What are sigma 1 and sigma 2? They are the absolute largest possible stresses, the absolute largest possible stresses that we can get normally. But look at this from a circular perspective. This point right here is the absolute farthest point over here, right? This point is the absolute furthest point over there. So whether you look at this from a trig perspective or look at it from a circle perspective, you get the same response. You get the same answer. Make sense? Now, here's something I didn't tell you before, but let me ask you this. This point right there, I propose that this point right there, that is tau max. That's the absolute highest shear stress that we get, right? What is tau max? It's the radius. right? Now, here's something that's kind of wild. What is the normal stress at this point? -2. Everybody okay with that? Watch this. Let's go back to this. Oh, that's not what I wanted. Now I gotta find my spot. What is the maximum? Oh, that's not. What is the maximum shear stress? 9.43. And look what happens to the normal stresses. Watch this. At that point, the normal stresses are equal. What are they? Maybe -2? Oh, we're not done. We're not done. Watch this. This is cool stuff. Okay. What was our initial state of stress? It was sigma x is what? Positive, what was it? +6. Sigma y is -10. Tau xy is -5. Was that about right? Check this out. Okay. I want to look at this particular point right here. I want to look at that particular point right there. Why do I want to look at that point right there? Because I propose that the coordinates of that point are 6 minus 5. Here's the origin, right? There's the origin right there. That's -2. This is 7. So 6 is about like that, right? 5 goes down. That's that point. Why am I picking 6 minus 5? Because that comes from the state of stress. Let's ask a question. What is that angle? What is that angle? Well, let's see. Well, now hold on before you do the -6. Hold on. What is this distance right here? This is 8, right? What is this distance right here? Well, just as a distance, it's 5, right? So what is that angle? And what is that? What's that angle? 32 degrees. Anybody else getting 32 degrees? So you're telling me that this angle is something like 32 degrees. Well, I propose I have this written incorrectly because it's not the angle. It's 2 times the angle because of all those 2 thetas that kept popping up in our derivation, right? So what is theta? 16 degrees, right? Think about what that means. This is just some random arbitrary state of stress. And I propose you have to rotate 32 degrees to get the principal state of stress. You want something else that's really wild? Watch this. I propose that the coordinates of that point are -10 and 5. The shear stress, yeah, it has an opposite sign, but because it's sort of the radius of the circle, it doesn't really matter. But where does the other stress come from? There's the -10. So there's your state of stress. So here's another way of thinking about it. As you rotate your coordinate system, you're just changing the coordinates of those points on the circle. And if you rotate to a theta value of 16 degrees or a 2 theta value of 32 degrees, there's your principal stresses. What do you think? This tends to be like the most complicated topic in this class. I've talked to folks who've been engineers for 20 years. They're like, I never could figure out Mohr's circle. I just couldn't get it. I didn't get it. So I spend a good bit of time in this class going through the trig and going through the math and sort of taking my time with it because I want you all to get it. Okay? Mohr's circle is not something to be scared of. If anything, it's supposed to make your life a whole lot easier when analyzing states of stress. You're taking a complex state of stress and all you're doing is plotting points on a circle and you can look at that state of stress at another orientation. Why does it matter? Because as the designer, what we need to know are the worst case normal stresses and the worst case shear stresses. And you don't necessarily need to actually plot Mohr's circle to do that. But you do need two quantities from Mohr's circle to get that. You need the center of Mohr's circle and you need the radius. From this plot, I propose to you that for any given two-dimensional state of stress, the maximum worst case normal stresses are the center plus the radius and minus the radius. And the worst case shear stress is the radius. That is always the case. And that's why Mohr's circle is so valuable and is such a nice analytical tool for engineers. It makes your life a lot easier when you have really complex states of stress. There's even a way of drawing Mohr's circle for three-dimensional states of stress. I'm not getting into that. That's a grad school topic or an intermediate or advanced mechanics topic. It's not hard. It's just we got other stuff to talk about. So. No, you don't do it in spherical coordinates. What ends up happening is instead of having a sigma 1 and a sigma 2, you have a sigma 1, sigma 2, and sigma 3. And it ends up kind of looking like this. Like you have, let's say, a circle like that, and then you'll have, a smaller circle, and then like a smaller circle, or another circle like that. Please forgive my artwork, because that's horrible. But that's kind of what 3D Mohr circle looks like. And then each of those radii have different meanings and whatnot. So yeah. Of course, to analyze a three-dimensional state of stress and to determine principal stresses in 3D, it's a completely different scenario than this. It's not as plug and chug. Well, I mean, it is, but the formulas get a lot more intense. And then in order to actually do it in a simpler fashion, you throw out some matrix math. Like, have you all ever heard of eigenvalues? So it's kind of like it's an eigenvalue analysis, and that ends up making it a lot easier. So, but I'm going to leave it at that. So. But then there's vectors and all sorts of stuff. So. Sound good? Okay, all right. So let me sort of explain what's going to happen on the video, because I don't want to dive head first into this stuff right now. But I do want to say a couple things before I get forward. So ultimately what we're going to do is we're going to use Mohr's circle and the concept of states of stresses to look at some real world examples. And so the real world examples are basically some beams. And then remember that stuff I mentioned earlier? What if you have a member that's yanked on and twisted and bent and all that? Well, I'm going to take that concept and extend it into a Mohr circle analysis, and I think you'll find it's really simple. The only other thing I wanted to mention about Mohr's circle is this. So Mohr's circle and the concept of transformation have applications far beyond stress transformation. You can use them for strain transformation as well. The only thing to keep in mind is in the realm of strain transformation, you have to use a half of your shear strain instead of the actual strain value. we could be here all day just explaining the inclusion of that half term, and I'm not going to waste your time doing that. Just trust me, throw in the half for your shear strains. It's a discussion in and of itself. Another thing that you can use Mohr's circle for is actually for moments of inertia. So let me sort of explain what that is. Let's say that you're analyzing something like, let's keep it simple. Let's say that you're analyzing an I-beam. Well, an I-beam expresses or has degrees of symmetry. So you as the engineer don't really need to figure out which is the best way of orienting that I-beam. You either put it this way or that way, and then it is what it is. But what if you're analyzing something like an airplane wing, where the cross-section is not pretty. It's very non-symmetric. So you can take its moment of inertia about the x-axis and its moment of inertia about the y-axis and its product of inertia to actually determine the optimum orientation. Like, what's the best way of turning that element so that you get the best stiffness out of it. And you're basically using Mohr's circle. Now, in fairness, the sign conventions are a little different. Like, you have to throw in some pluses and minuses and whatnot. And that's just, you just refer to the textbook to see why. But by and large, the transformation philosophy is very similar. So you can use stress transformation principles for strain transformation and for optimum orientation for cross-sections. Just be cognizant of your sign changes is all I'll say. Now, what we're going to do in the video is I'm going to look at a problem like this. Okay, so here's a beam, right? Okay, would you agree that that beam's going to have a shear diagram and a moment diagram? So I propose that at this particular point right here, and I'll go through this in the video, but there's going to be a normal stress and a shear stress. So what's the worst case scenario? Basically, what is the worst case scenario for normal stresses and shear stresses? And that's a very realistic evaluation for you as an engineer because, and I say this for really for civil engineers and mechanical engineers. Let's say that this is a real beam in a real system, be it a bridge, a building, a car, what have you. And let's say that that car or that bridge has been in service for a while, what have you, and you're looking and by golly gosh gee, there's a spot of rust right there. Okay? So that point on that beam is weaker than the rest of the beam. So maybe it's worth evaluating the stresses. Now, it's pretty easy to see, you know, here we know the worst case scenario is compression on top and tension on the bottom. But right there, maybe not the case. Maybe there, you know, the worst case scenario is the coordinate system rotated like that. And so that stress can be higher than what you expected when you initially designed it. So we're going to use the Mohr's circle philosophy to determine principal stresses and maximum shear stresses at that particular point. And then we're going to look at this problem where I have a 4-inch circular steel shaft that's being pressed on, twisted, and bent. What are the principal stresses and maximum shear stresses? So what we'll basically be doing is using each of these philosophies that we've already discussed. You know, how do you determine twisting stresses? How do you determine bending stresses? How do you determine axial stresses? And then take those stresses and then apply Mohr's circle and stress transformation to determine worst case scenarios. And so I think that'll tie it together a bit. Then what we'll do when we come back is we'll discuss pressure vessels, which is arguably probably more important to you mechanical folks. However, there are some applications in civil engineering where understanding pressure vessels is kind of important. If you're designing a reinforced concrete column and you need to detail the spiral reinforcement in that column, basically you treat that spiral reinforcement as if it was a pressure vessel trying to contain the column. So the math is very similar. So once we get through pressure vessels, it's going to be very quick. The derivation is really simple. Then we get into column buckling, and that is it for this class. Unless you want me to talk about more. I can throw more on the exam if you want. You're like, okay, it was funny in like week 3, week 4. Dude, Dr. Mike, like, we've had it with your cheesy dad jokes. That's oh. Suddenly see Mohr's circle, right? My wife would love that. She's a big Little Shop of Horrors fan. All right, so I just want you all to see what's happening, you know, between now and the end. So just to be clear on housekeeping, you all have turned in homework. So just to recap, you all have turned in homework 6. Homework 7 has been uploaded today. It's not due till after break, but I actually would take a look at it because if you like, screw it, I'm not going to look at it till the 28th. Some of that stuff that's on that assignment, we've been talking about now. And if, all that tryptophan from all the turkey causes you to forget a lot of this stuff. So I highly recommend that you take a look at it. So again, you turned in homework 6. Homework 7's due the 29th. On the 29th, they'll give you homework 8. It's due the 6th, and that's it. As for lecture or meetings together in class, we're meeting today, and then we're done. I'm going to post a video, so we are not going to meet together in person on the 15th. You just watch the video. So I'm not seeing you all until after break. I can see that you're heartbroken over that it's causing you to get emotional. It's okay. See about that. First off, let's say a couple things about that. You just freaked everybody out in here because the folks that don't have structural analysis are like, what test tomorrow? What are you talking about? The way to look out for their emotional stability. I'm just kidding. No, you do have to be here tomorrow. Well, actually, no, you don't. You can skip it if you want. You can do whatever you want. There's just consequences, You can go rob a bank if you want, but it won't be much longer after that. At least not for you. So that's it. I wish you all an absolutely wonderful and pleasant Thanksgiving break. I will see you all in 2 weeks. That's right, 2 weeks. It's the 13th, and I don't see you all till the 27th. Enjoy it. That's all I got. I'll see you. Although I do need my sign-in sheet. So I do need that.